everyone, welcome back to my channel. Today we're going to go over some of the most important principles in all of physics, Newton's laws of motion. These laws are some of the most foundational discoveries in the last 500 years and are frequently used in physics and engineering. They include the law of inertia, force is equal to mass times acceleration, and the law that states that every action has an equal and opposite reaction. You've probably heard of at least one of them, but not how they were found. Which makes sense since these laws are mainly taught in freshman year in middle school, and they were derived with calculus and rotational motion. Good news though, I'm here to teach you how they are found. Don't worry though, I'm not going to teach you calculus in one video. In fact, I'm going to make sure not to use any in case you don't know it. Also, if you're trying to learn calculus in one video, I'm sorry, but you're kind of in the wrong place. Also, that's going to take you way longer than a couple minutes, so let's start by looking at the man who the laws are named after. Isaac Newton was born on January 4th, 1643 in Woolsthorpe, England, and was raised on a farm. He went to King's School in Grantham and later graduated from the University of Cambridge. Newton was very introverted and preferred to keep to himself and focus on his studies. He studied the work of Aristotle and was able to join the world of science during the Scientific Revolution. For those who don't know, the Scientific Revolution was a period in time when scientific discovery was booming. It was a great time for lots of young English scientists, like Newton, to enter the field. There was just one problem: plague. Being the smart person he was, Newton decided to avoid the plague, and people in general, by going home to his farm. It was so peaceful that he'd sometimes sit under an apple tree to read. One day, he got hit in the head by a falling apple. That was weird. I wonder if that led to any discoveries that would change the world of science forever. On the bright side, he got lots of time to study stuff like planets and their orbit. In fact, very recently, the world had discovered that the Earth wasn't in the center of the solar system as initially thought. In actuality, the sun was in the center and the Earth orbited it. This led to Newton reading about Galileo Galilei's study of motion. Galileo also studied Aristotle, who believed that objects needed an external force to keep up uniform motion. Galileo believed that he was wrong about this, and decided to conduct his own experiments. He found that objects would move farther on smoother surfaces rather than rougher surfaces. Usually the rougher surfaces had more friction. This led him to theorize that without any friction or other outside forces, the object would move forever without stopping. However, this idea had one little problem. If Earth was in motion, why didn't it, or its people, go flying off into space? After all, nothing was holding anyone down. But, he wasn't flying off into space, and neither was anyone else, so something had to be up. Unfortunately, Galileo died before ever figuring out the answer. But a year after dying, Newton was born, and when he discovered gravity, he realized that Galileo's theory on motion was correct. It's just that gravitational force was keeping people from flying off the Earth. And it was also keeping the Earth from falling out of orbit around the sun. Looks like the apple did revolutionize science. This helped Newton prove Galileo's theory about what would have become the first law of motion. An object in motion will stay in motion unless an outside force is applied, otherwise known as the law of inertia. But wait, why didn't the Earth just fly into the sun if gravity was keeping the two attracted to each other? Well, that's where the second law came in. Decades earlier, a man by the name of René Descartes was also studying Aristotle and Galileo's work, and formulated that motion could be conserved in a system, or isolated set of objects. He found that the motion, or momentum as it would later be called, could be mathematically portrayed as size times velocity. Unfortunately, he believed that the size came from an object's volume, or surface area, which actually had no effect on its momentum, so he got that part wrong. Thankfully, Christian Huygens, another physicist, would discover that and eventually realize that instead of size, the correct measurement needed was mass, and finally formulated the law of conservation of momentum. That law would then be expanded by Christopher Wren and John Wallis, both of whom would find specific collisions where momentum could be conserved. When Newton discovered this law, he found that the momentum would only change when an outside force was applied. Studying calculus, which in simple terms is the math that has to do with rates of change, Newton reasoned that force had to represent the rate of change in motion of an object, and wanted to show that mathematically. To visualize, think of a ball rolling on a surface with no friction. According to the law of inertia, it's going to keep moving with the same momentum, which is made up of mass times velocity. Now imagine that ball experiences a push, or an outside force. That push isn't going to take away any mass, so the mass stays constant, but it will change the velocity, meaning that the force is applying an acceleration to the ball. Acceleration is the rate of change of velocity, for those who don't know. So to find the force, we need to take the mass and the acceleration and multiply them by each other. And there, you have mass times acceleration is equal to force. Of course, there could be multiple forces at once. Let's say there's a second force applied to the ball. In that case, it would have to have its own acceleration on the ball, and both accelerations can be added or subtracted from each other depending on the direction of the force. In this case, it would be subtraction, since the arrows are going in the opposite direction. So we would say that sigma force, or the total force on an object, is equal to mass times the total acceleration. These calculations are how Newton found the equation for force. It also helped him discover why the Earth was orbiting around the sun and not, flying into space. It's because the Earth was being held down by something called centripetal acceleration, where there's acceleration perpendicular to initial velocity. Both velocity and acceleration are vectors, so when they're perpendicular, the acceleration doesn't change the velocity, but it does mean that Earth is constantly moving in a direction that won't let it crash into the sun. So instead, it'll just constantly move around it. Yay! We solved this problem! But wait, there's one more! Let's say that an outside force is another ball, and it hits that ball. Well, that ball is going to get accelerated by that force. What about the other ball? Thankfully, that answer would also come from momentum. It started as a theory by Johannes Kepler, who reasoned that force could act on two bodies at once. He was right, but he couldn't prove it mathematically. Then the conservation of momentum was discovered, and when Newton found out about it, he was able to prove it. You see, when momentum is conserved in a system of two spheres colliding with each other, their momentums change by the same amount. This was because the total momentum stayed the same, so when one momentum increased or decreased, the other would change the opposite way by the same amount. Let's take two spheres with an equal mass. When they bump into each other, their total momentum is conserved. But when sphere A loses 5 kilograms meters per second, sphere B gains 5 kilogram meters per second. Essentially, their momentums change by the same magnitude. And since, as we just discussed, force is the rate of change of momentum, that means that the force applied to both objects have equal magnitudes. However, when one momentum decreases, the other one increases, meaning that the forces are accelerating them towards opposite directions. This led Newton to reason that when one object applies a force on another, that object gets an equal and opposite force applied on itself. You can actually test this out by tying two strings of equal length to the same point, attaching two small spheres of equal mass onto each end, and releasing them from the same height directly across from each other. The two spheres should collide and then rise to the same height as each other, but make sure that this is done in an open area and that the spheres are tied tightly. If you aren't careful about it, then those spheres can hit something, and that something can be you. And I'm guessing you probably don't want that. Either way, Newton was finally able to prove his three laws of motion, and ended up publishing them in 1684 in his Philosophiae Naturalis Principia Mathematica. And I probably butchered that, I can't speak Latin. In English, it's called the Mathematical Principle of Natural Velocity, but it's usually referred to as the Principia. You can actually find an English translation on Amazon. It's really interesting. It's got lots of stuff on gravity too, if you're interested in that. So, why was this important? Well, since this discovery, many physics principles were derived based on these laws, and continue to be today, making them the foundation for lots of modern-day science. It also helps engineers come up with new ideas that help our society progress in terms of technology. For example, rockets work by propelling lots of force onto Earth and air below it. Using the third law, the force that's propelled by the rocket creates another force that pushes it upward, despite it being so heavy, giving it the ability to fly. You've probably also noticed that Newton didn't come up with these laws completely on his own. He took a lot of theories from past physicists, proved them, and published them. This actually happens a lot in the world of science. Scientists will take former concepts and fix or prove them, turn those concepts into their own. In fact, many scientists use Newton's laws to prove their own work. If we want science to progress, people need to borrow from the past, prove older ideas, and create new ones, just like Newton did. Thank you all for watching. I hope you enjoyed that. I just wanted to tell you guys that I'm going to post every other week instead of every week. I know I said I tried to post every week in my intro, but I kind of underestimated how much work this would be, so I'm going to go by a bi-weekly schedule instead. Please comment on what you thought of my video and what you want me to do in the future. Go ahead and like and subscribe, and I'll see you all in 2 weeks. Bye!